Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from June 2023, Paper 4, Variant 1. In the last few videos, we have already discussed from question 1 to question 5, and today's lesson, we will start from question number 6. We will talk about electromagnetism, we will also discuss about quantum physics, and we will also talk about medical imaging. Especially, we will discuss a beautiful question on ultrasound. Let's study together, let's improve together. Question 6 part A says, state what is meant by a magnetic field. Magnetic field simply is a region around a magnetic pole, or we can say around a moving charge, or simply we can say around a current carrying conductor, means current carrying wire. If in that region we bring another magnetic pole, or we bring another moving charge, or we place a current carrying wire in that region, wire or current carrying conductor will experience a force, and that region we call is magnetic field. Let me show you the answer, how you can write down your answer. This is how you can write down your answer. In your answer you have to mention a region where a force acts on a magnetic pole. You can also say force acts on a moving charge, or you can say force on current carrying conductor. So any one of them you can mention in your answer. And this question has 2 marks. First mark is the M mark. You must have written a region where a force acts on, and then if you write down magnetic pole, or if you write down moving charge, or if you write down current carrying conductor, you will get 2 marks. Part B says a long straight wire P carries a current into the page as shown in figure 6.1. On figure 6.1, draw 4 field lines to represent the magnetic field around wire P due to current in the wire. So first thing we need to understand, this current is into the page. We have current and we need to find out direction of magnetic field. So simply we can write down here, we have current and we need to find out magnetic field direction. So we need to find out magnetic field direction. So we have one quantity and we need to find out direction of another quantity. For that purpose we have to use right hand grip rule. So simply we will write down here which hand you have to use. We have to use right hand grip rule. So this is, we need to use right hand grip rule. And right hand grip rule, so this is my right hand, you can see current in this case is into the page. So like this, current is into the page, so the magnetic field is clockwise. So magnetic field is clockwise, so I can write down here magnetic field is clockwise and current is into the page, so clockwise. So you have to draw lines clockwise. So let me show you how you can draw the magnetic field. So this is how you can draw the magnetic field. But one thing you have to be very clear, the gap between the lines, mean this gap, it has to increase, it has to go on increasing. Actually this question is asking you to draw 4 field lines. I have already drawn 3 here. We can also draw another one. We can also draw another one like this. So these 4 field lines, this is how you need to draw 4. But one thing we have to be very clear, as I mentioned before, the gap, this has to increase. You see this gap is shorter, this gap is wider, and this one is the widest. This is telling us that magnetic field, as we go away from the wire, magnetic field get weaker and weaker. So this has to be in your answer. Part C says a second long straight wire Q carrying current of 5.0 amps out of the page is placed parallel to wire P as shown in figure 6.2. The flux density of the magnetic field at wire Q due to current in wire P is 2.6 millitesla. Calculate the magnetic force per unit length exerted on wire Q by wire P. Exerted on wire Q. And it is also given to us the magnetic field due to wire P near Q, we can simply say BP. This is equal to 2.6 millitesla. We can say BP. We need to calculate force. So magnetic force means the force on Q. this will be equal to BIL. For this question, we need to calculate magnetic force per unit length. So simply we can write on here F on Q by P divided by L. This is equal to BI. But here is one very important point we need to understand. We are talking about force on Q. So we have to consider magnetic field due to P, external magnetic field. So if I write on here, so this one is the external magnetic field. So external magnetic field here is due to wire P, and this is current in wire Q. Now simply we need to plug in values. We have magnetic field due to P at Q, that is 2.6 millitesla, 2.6 times 10 to minus 3, and value of current in wire Q. In wire Q, the value of current is 5.0 amps. So we can write down this is 5.0 amps. Now if we multiply this one, we will get 0.013 newtons per meter. So this is our final answer up to 2SF. And this question has 2 marks. The first mark you will get if you have written this formula. For writing this formula, you will get 1 C mark. And if you have got the right answer, you will get an other mark. If your answer is correct, you will get 2 marks. But if your answer is wrong, but you have written the formula, you will get 1 mark. Second part says state direction of the force exerted on wire Q by wire P. So we have to consider the force on Q by P. So let's try to understand the formula first of all. So F is equal to BIL. So we need to understand which magnetic field we have to consider. So we need to consider the external magnetic field, means magnetic field due to P, and we need to consider current in Q, and L has to be the length of Q. Now if you look at wire P, current for wire P is given, that is into the page. So the magnetic field at this point due to P, this will be downward. So this is the magnetic field. So you can use your right hand. So if you turn your fingers, if you curl your fingers, you will see magnetic field at this point is down, and current in this wire is out of the page. So now you have to use Fleming left hand rule. Fleming left hand rule. So if we use Fleming left hand rule, we have magnetic field that is down, and we have current that is out of the page. So we can write on here, we have B, this one is down, and we have current that is out of the page. So the force will be to the right. So this is one way you can find out direction of force. Another way to find direction of force is, as current in this wire is into the page and current in this wire is out of the page, these two currents, they are in opposite directions. It means these two wires, they will repel each other. So the force on this wire will be to the right, and force on wire P will be to the left. But for this question, simply we need to find direction of force on wire Q. So simply we can say this is to the right. Third part says the flux density of the magnetic field at wire P due to current in wire Q is 1.5 millitesla. It simply means that we have BQ, and BQ is equal to 1.5 millitesla. For this question, we need to determine the magnitude of current in wire P, and also we need to explain reasoning. In order to answer this question, the first thing we need to understand, whenever we have two wires and they carry current, force on each wire is the same in magnitude but opposite in direction. It simply means that if we write down here force on P due to Q has to be equal to force on Q, and these two forces, they have the same magnitude but they are in opposite directions, and this is based on Newton's third law. So simply we can say it is based on Newton's third law. So this is the reasoning. Question was asking you explain your reasoning. So this is our reasoning. Now simply we need to use F is equal to BIL. F is equal to BIL. We need to determine in this case current in the wire, but in the last part we have already calculated force per unit length. force per unit length. So simply we can say this is equal to Pi. This P is the external magnetic field, mean this is due to Q, and I is current in P. So this value we have already calculated, and that was equal to 0.13. So here we have BQ and here we have IP. For this question we need to calculate value of IP. So simply this will be equal to 0.013 divided by BQ, magnetic field due to Q, and we have here that is 1.5 millitesla. So we have 0.013 divided by 1.5 millitesla. If we solve this one, we will get our final answer is 8.7 amps. So this is current in wire P. So simply we can say 8.7. And this question has 2 marks. The first mark you will get if you have written the first statement, and this is the B mark, I mean this one has to be in your answer. And the second mark is the answer mark. If you have got the right answer, you will get 2 marks. Question 7 part A says, state what is meant by de Broglie wavelength. De Broglie wavelength simply is equal to H divided by P, or we can say this is H divided by M times V. It simply means that if P is very small, lambda will be very long, means it will be detectable. For example, for electrons, wavelength is detectable. But for human beings, as the mass of human beings is very high, it means lambda is very short, and that is not detectable. That's the reason we appears like a particle. But mass of electron is very small, and electron can be detected by different experiment like electron diffraction. We can observe electron behaves as a wave. So simply we can say wavelength associated with moving particles. So this is simply you can write down, and if you write down in your answer you will get 1 mark, and this is B mark. In your answer you have to write down moving particle, because if V0 it means lambda will be equal to 0. So you have to mention moving particle. Part B says figure 7.1 shows a glass tube in which electrons are accelerated through a high potential difference to form a beam that is incident on a thin graphite crystal. So here we have thin graphite crystal. After passing through the graphite crystal, the electrons reach the fluorescent screen. The screen glows where the electron strike the screen. Figure 7.2 shows the fluorescent screen viewed end on from the right hand side of figure 7.1. State the name of the phenomenon demonstrated by the pattern shown in figure 7.2. So in this case we can say if electrons they behave as a particle, we should see only electrons right in front of this beam of electron. We should see electrons here, means we can expect electrons here. But in this case electron they spread out, so it simply means that this is demonstrating electron diffraction. So this is diffraction. So in our answer simply we can say this is electron diffraction. For the second part we need to explain what can be concluded from the pattern in 7.2 about the nature of electrons. So in this case electrons they diffract, and only wave can diffract. Diffraction is a property associated with waves. So in this case electrons are behaving as wave. So this is we can write down for the second part. So for the second part we can simply say beam spreads out indicating diffraction. So electron beam is behaving as a wave. So if you write down these 2 points you will get 2 marks. Part C says the electrons in B are now accelerated through a greater potential difference between the cathode and anode. On figure 7.1, sketch the pattern that is now seen on the fluorescent screen in figure 7.1. So in this case potential difference has been increased, so it simply means that the kinetic energy of electrons will increase, So here we can write down kinetic energy. If potential difference increase, it means kinetic energy will increase. And kinetic energy we can write down in this form. We can write down P squared divided by 2m. So this is Q times delta V. We can simply derive this one. So this is very simple derivation. We can derive this. Simply what you need to do is kinetic energy is equal to 1/2 mv square, and momentum, this is equal to mv. From here we can get value of v. We can say v is equal to p divided by m. And now if we plug in this one back inside here, we will get p squared divided by 2m. From here we can write down p. This will be equal to 2m times q times delta v, root of this. So you can see here, if potential difference increase, it means momentum will increase. Now we can write down de Broglie wavelength. This is equal to Planck's constant divided by momentum of particle. So if momentum of particle increase, it means lambda will decrease. If lambda decrease, it means spacing decreases. Spacing decreases. So we can say spacing decreases. So rings are close to each other. So we can say rings get closer. So rings get closer. Now let me explain you this one with one simple example as well, with the help of diagram. You can see here, so this is the diagram, and you can see we have another diagram here. This is at low speed, this one is at higher speed, means these rings are close to each other. So now we need to draw the rings on this one, but they have to be close to each other. So simply you can draw like this. So this is very important point. Most of the time they will ask you in the exam. For the second part, we need to explain with reference to de Broglie wavelength the change in the pattern on the fluorescent screen. Actually, we have discussed this point in the last part. Let me recap some important points. We have discussed that momentum is equal to 2m times q times delta v. Delta v is the potential difference. So if delta v increase, it means momentum of the particle will also increase. Then lambda has to decrease because h is the Planck's constant. If momentum increases, wavelength has to decrease. If wavelength decreases, it means the fringe spacing, it has to decrease. If we are using the same graphite crystal, mean same grating spacing. If you're using, or simply we can say if you're using the same graphite crystal with the same grating spacing, diffraction angle will decrease, or simply we can say fringe spacing will decrease, as you can see here. So this is at low PD and this one is at high PD. So we can see this spacing, this decreases. So these are the points you have to write down in the answer. Let me show you the answer. In your answer, you can mention these points. First of all, you can say greater PD. It means greater momentum, as you can see from this first point. Second, greater momentum, so decrease in de Broglie wavelength. So you can say greater momentum, decrease in de Broglie wavelength. Smaller de Broglie wavelength for the same grating spacing, means if you're using the same graphite crystal, causes smaller diffraction angle, mean fringes will be close to each other, or you can say decrease in fringe spacing. In diffraction pattern, mean fringes will be close to each other. So these points you need to write down. These are kind of standard points, so it's good to master them. You can start with this one, momentum, then you can go to lambda, then you can say if lambda is small, fringe spacing will decrease. Question 8 part A says table 8.1 shows some data relating to the properties of air, gel and body tissue. The data are given to 3 significant figures. For part A1, we need to show that specific acoustic impedance of gel is 1.68 times 10 to 6 kgs per meter square per second. Acoustic impedance, we use letter Z for acoustic impedance, and this is the product of density of medium times speed of ultrasound in that medium. In this case, we are talking about gel. Density of gel is 1200 and the speed of sound in gel is 1400. If we multiply this one, we will get 1.68 times 10 to 6 kgs per meter square per second. So this is the answer. For the second part, we need to complete the table 8.1 by calculating the missing values to 3 significant figures. Use the space below for any working that you need. So if you look at this table, we have here density is given to us, speed of sound is given to us, and acoustic impedance is given to us. For the first row, for air, we need to calculate density of air. And density of air simply will be equal to acoustic impedance divided by speed of ultrasound in air. So Z we have, this is equal to 440 divided by 340. We will get 1.29, 3 significant figures. So we can write on here 1.29. For the second part, for gel, we need to calculate Z. We need to calculate acoustic impedance. Z is equal to rho times C. Actually, we have already calculated here. So we can write on here, this will be equal to 1.68 times 10 to 6. Same, we have already calculated. So we can say this is 1.68 times 10 to 6. And for tissue, we need to calculate C. So we can write on C for tissue. C for tissue will be equal to acoustic impedance divided by density of tissue. Acoustic impedance is equal to 1.68 times 10 to 6. Simply we need to divide this one by its density, that is 1090. And if we solve this one, we will get 1540 meters per second. So this is the speed of sound in tissue. So we can write on here 1540 meters per second. So this is how we can answer. Simply for this part of the question, you need to understand this formula. Simply you need to understand this. You need to understand acoustic impedance is the product of density of the medium times speed of sound in that medium. Part B says use the information in A to calculate the intensity reflection coefficient for A tissue boundary and for gel tissue boundary. For A tissue boundary, we can use alpha sub r. It means we are talking about intensity reflection coefficient. This is equal to Z1 minus Z2 square. Z is representing acoustic impedance divided by Z1 plus Z2 square. So we are talking about air and we are talking about tissue. So we have, for tissue, we have value of Z, that is equal to 1.68 times 10 to 6, minus for air we have 440. So this is 440, then square of this, divided by Z1 plus Z2. So we have 1.68 times 10 to 6 plus we have 440 square of this. And if we solve this one, our answer will be very close to this value. We will get 0.999. So what this is representing, if value of alpha is equal to 0.999, means it's very close to 1. It means that most of the ultrasounds, they will be reflected back. So they will return back into air. So this is the meaning of 0.99. And this question has 2 marks. The first mark you will get if you have entered these values, means you will get the C mark here, and the final is the answer mark. If you got the right answer, you will get this mark. Means 1 mark is for writing the formula, 1 for calculations. And so in this case, if the ultrasound are traveling from air, so let me draw here. So let's say this is the air and here we have the tissue. In this case, ultrasounds coming here, most of the ultrasound will be reflected back, most, and very little it will enter the tissue. So this is meaning of 0.999. Gel tissue boundary, we need to use the same steps, but we have just different numbers. So we can write down alpha r for this one, means intensity reflection coefficient. Again, we can write down the formula Z1 minus Z2 square. Always write down the formula, divided by we have Z1 plus Z2 square. We are talking about gel tissue, so we are talking about gel, we are talking about tissue. For the gel, we have this is 1.68, for the tissue also 1.68. So we have 1.68 times 10 to 6 minus 1.68 times 10 to 6 square of this one divided by, we have 1.68 times 10 to 6 plus we have 1.68 times 10 to 6 square of this. And if we solve this one, we will get 0 divided by this. So we have divided by 1.68 times 10 to 6 plus we have 1.68 times 10 to 6 square of this one. So in this case we will get 0. So it simply means that reflection is 0. So if we try to understand this one with the help of diagram, we can say these are the incident ultrasound waves and these are the ultrasound waves. They will enter the tissue. So in this case, as alpha is 0, it means all the ultrasound, they will enter the body tissue. So this is what we want, and that's the reason we use gel on the body, on the belly of moms for better results. Very nice question. So you need to understand, why do we use gel? Because we want most of the ultrasound to enter the body and contribute to image formation. Part C says, use your answers in B to explain why gel is applied to the skin during ultrasound scanning. Actually, we have discussed this point in detail. Why do we need to apply gel? So you can see here we have, this is ultrasound. So this is ultrasound transmitter, and you can see gel here on the belly of patient. So why do we use this gel? We have discussed this point in detail in the last part. Now I will again highlight some point and then we will be able to write the answer. The reason is that because gel and the body tissue, they have same acoustic impedance. So they have almost same acoustic impedance. Means same value of Z. If same value of Z, it means that alpha R, intensity reflection coefficient, this is close to 0. So it simply means that most of the ultrasound, they will enter the body of the patient and they will contribute to the image formation. And we can have better image and we can easily see details of the parts of the body inside the body. So these are the points we need to understand, and this question has 2 marks. So in this case, let me rewrite one thing again. So if this one is the gel and this one is the tissue, here we have the tissue, and if Z is the same, in this case most of the ultrasound waves, they will enter the tissue, because in this case alpha R is close to 0. So we can get better image, so we can study the internal body parts in more detail. So let me show you the answer, how you can write down your answer. So in your answer you have to mention these 2 points. The first point, you can say without gel, almost all of the incident ultrasound is reflected from the skin. So we can draw here, for example, if no gel, then here is air and here is tissue. We have done calculations, you can check the previous part. So in this case, most of the ultrasound will be reflected back. Very little will enter the body. So in this case we cannot get a better image. So image will be blurry, we can say blurry, and here we will get clear image. So we will get clear image. So this is one point you can write down. With gel, we can say almost all of the incident ultrasound is transmitted into the body. So we will get clear image. So that's all for today's lesson. I hope you have better understanding of electromagnetism, you have better understanding of medical imaging, and also you have better understanding of quantum physics. So that's all for today's video, and if this video was helpful, please like and subscribe, because your encouragement is very important. I'll see you in next video.